This is Jeff Mauk, technical sales engineer with Accumold in Ankeny, Iowa. And this webinar that we're talking through today is in regards to designing plastic parts for micro injection molding. Some of the things that as a designer at the 101 level you might want to consider. Today we're going to talk about wall thickness. We're going to talk about parting lines, draft. We're going to talk a little bit about subgates, ejector pins, slides, and last but not least, talk a little bit about surface finish. And we're going to do so on this part that I'm showing you on the screen. Just a little bit of information before we get kicked off here. This model used in this presentation today was created for this webinar and is not actually a customer model and or a part. Accumold respects our customer's intellectual property and would never show a part without permission from the customer. And so with that, let's get started here. So this part is a coupler part, if you will, maybe something that you'd stick into this side and that side and couple something. It's a completely made up part, but I think there's a lot of geometry in here that will help to teach about some of the things that we want to talk about today. And so what I'm going to do is I'm going to slide this up here. And this is basically, as a designer, the overall shape of the part. And what we want to do is kind of walk through some of the steps in the feature manager tree of this part and maybe talk about some of the details of where this part needs to go relative to the tooling that we're going to create. I'm just going to quickly flip through there. And so with this particular item, what I've decided is that I want the parting line for this part to run right through the waist in the center. That's what that line represents. And then also I'm going to add a little bit of draft. And now you notice that I added draft to this side, but I didn't add draft to this side. And it would be a good time to tell you that I'm trying to treat the bottom of this part, or the part that goes into the B side of the tool, as what you should do. And then up here, it's probably obvious that this is maybe what you shouldn't do in a micro injection molding. So we'll continue on, put draft on the bottom so it can eject a little more easily with less force. Then the next item that I did is I cut a circular opening in this part. And we've determined that in this particular part, for its end form, fit, and function, that we want this thing to be about 10,000ths of an inch thick. And so this wall out section right here is 10,000ths of an inch, except for in these areas right here. We'll visit that again a little bit later in our conversation. Then I roll down one more feature, and you'll note that we did this side a little bit differently. And you'll note that we still have that 10,000ths wall thickness, but we don't have those extra thick areas on this side as we had on that side. So we'll continue to roll through here, and you'll notice that we're adding a rib to the outside. This rib is going to serve us in two ways. It's going to provide us with a surface for ejector pins and also a flat surface for a subgate, which we'll talk about in just a few seconds when we do a quick animation for the tool. And so that I took that rib and I patterned it around the outside edge, so you can see those ribs. And you might also notice that as you look down the surface here, that these are actually drafted as well. So I've added draft to this outside surface, I've added draft to this inside surface, and all of the ribs have draft as well. And then at the top, we have nothing. It's a straight wall. Doesn't mean that it can't be molded. Just it would be better if everything that you had draft on it. Then additionally, what we're going to do is we're going to add a location where we think we want our subgates to go. This red dot represents where the opening in the cavity wall will be, where the molten resin transfers from the runner through the cavity block and into the cavity that makes up this part. We'll see that in an animation in just a second. And so on the bottom, you'll see that we have some different colored surfaces here, and those magenta dots represent where I would intend to maybe put ejector pins on this particular part. And then I we'll talk a little bit about these areas here a little bit later in the presentation. And then also we'll talk a little bit about this feature, which is a hole and it's perpendicular to the parting lines. That's a good transition for us to then slide over to the tool that would make this part. Okay, so let's go take a look at that. So here's our tool. I'll give you a quick overview. This green block down here that's translucent is the B side cavity. And this block up here is the A side cavity. And inside of that is the part that we modeled. Okay. And then right here, we have the runner. And that's where the molten resin comes in and then drops down through that cone. And then there's an opening in the cavity to fill the part. And then, so we talked about the runner, and then all the pins down here in the bottom that are blue. The red one represents that it's an ejector pin for the runner, and these magenta ejector pins are a representation for ejecting the part. And last but not least, we have a slide. This represents a slide which has a core on the end of it that helps us make our hole in the side of the part. Okay, so we talked about an animation, so let's take a quick peek at that and we'll see how this tool would operate. So you see the slide sliding out, then the B half drops out, and then the ejector pins push the part out of the cavity. And so now when you put the part and all the components that we had together with how this tool is going to operate, maybe the geometry of the part would make a little bit more sense. We'll run that through one more time. Slides coming out, clearing the core for that hole. B side comes down, ejector pins lift the runner and the part out at the same time and then shear that gate off. So this for this runner and this part now are two totally separate components. What I want to do is go take a quick look at the B side cavity block. So here's that B side cavity block. This is where the runner, which was the red component in the tool assembly before, this is where the molten resin comes through. This area here is called the runner, and then this funnel here leads to the gate opening. And so you can see that cone there, and then you click on this surface here and you see that hole turn blue because it's showing that surface. And you can see that the gate is literally an opening in the cavity block that allows the molten resin to come into the cavity shape, and the cavity shape is that 3D solid model that we had created. Just to give you a little bit better view of that gate, the subgate. We'll do a section through this block. In fact, maybe we'll keep the cap colors on so it stands out a little bit better. And you can see where the ejector pins are coming up from the bottom, and that's where it would push off on the solid cooled part inside the cavity once it's done. And you can see this sharp edge. Now, when the ejector pins push the part out and also push the runner out, it will slice through the gate right here and automatically separate the runner from the part. And so a subgate is always the preferred method to produce a part if possible, simply because there is no post-mold interaction required of the part. After the part is ejected from the cavity and the runner is ejected, end of arm tooling will come in and grab the runner and dispose of that. It'll be reground and reused or disposed of, depending on what the material is and what the specifications are for the customer. But most of the time, 99% of the time, virgin material is required for micromolding in the fields that we work with. So it's reground and resold for use outside of our facility. But anyway, you can see a little bit more about how the part design has evolved based on how we want the tool to act. So let's collapse this back down and let's go back to our part just for a second. So I want to talk briefly about wall thickness. Modeling a part with uniform wall thickness should be your primary goal. And uniform wall thickness allows the tool cavity to fill uniformly. Uniform wall thickness allows the molded parts to cool uniformly. And parts that cool uniformly typically are more repeatable and they have a higher quality because they exhibit less surface imperfection and warp. So remember, we had the top half, what not to do, the bottom half, what to do. And I would just like to pause and talk about a little more detail. So because we just did a circle extrude and a cut there, it left a little bit of a thickness here, which is represented by these two triangles. And basically what's going to happen is that the heat in that area is going to remain there longer than the heat in these 10 thousandths thick wall sections. And what ends up happening is that there's a sink that gets created there, and that sink usually means that it's going to pull the geometry around the part with it, and then it'll create some warp in the part as well. And so as you're designing parts, just look for these wall thicknesses that have gotten a little bit thicker. And as a contrast, we look at this opposite side, and you can see that we literally have a 10 thousandths wall all the way around, except for where the ribs are. And so I would say that in this perimeter that we're about, I don't know, 90, 95% of the same and or uniform wall thickness with maybe another 5% where these ribs are. But in this particular instance, the wall thickness being 10 thousandths of an inch. Typically in micromolding, we try not to do an ejector pin smaller than 15 thousandths of an inch. It's a good point of reference for designing these small parts because anything, we can create them smaller, you certainly can, but repeated force of pushing this part out of the cavity could end up bending those ejector pins, and you'll be replacing them and have high maintenance. 15 thousandths, this is about as small as we like to go here at Accumold. And so we created those ribs so that we would have some surface area for those 15 thousandths diameter ejector pins to push that part out. And then also, additionally, as we saw in the animation, we found a location that was important for us relative to the gate. And two things about this location. Number one, this is a flat surface that we're going into. I know when you look at this surface and this surface, it looks flat as well, but it's actually, you know, a drafted radius. But in this particular instance, this surface truly is flat. It is, if you draw a box across the top, that bottom edge of that box shows you that this is a flat surface as opposed to round. And what that provides you is the ability for the gate to shear off cleanly and leave the smallest gate vestige that you can. So sometimes when you're designing a part, you have a round part and you don't see a need to add a flat, but having a flat for your subgate location is crucial to getting a clean part, to having a part that has a faster cycle time with no post mold labor to separate the runner and gate from the part. And so sometimes you might want to consider putting in a flat on a round part, even though that flat doesn't perform any kind of function in the end form, fit, and function of your design. It certainly provides a function for the manufacturability of the part, and that flat oftentimes doesn't cause your end form, fit, and function to suffer in any way, but just understanding the need for a flat for a gate can make all the difference as far as the manufacturability of a part and the cleanliness of that gate vestige during the molding process. Also wanted to talk a little bit about parting lines. We saw in that animation, and we'll just flip back to the tool quickly and we'll explode this again. But basically when I put the split line in the part, what I had decided then was that this surface, I'm going to go ahead and make these solid. Let's see here. There's that one, there's that one. So the decision, you know, that was made was that that surface and the opposite surface on the A cavity block here were going to be the parting line. And when we talk about the parting line, that's uh, the A cavity, B cavity, and when they open up, and that's where this cavity block splits from this cavity block or parts, thus the parting line. And anytime that you can pick a parting line on your part that is simply an open and a close, that's your simplest, most cost-effective methodology to do injection molding. It's when you introduce features like this hole, which has an axis that runs perpendicular to the open and close axes or the parting line axes, that you start increasing the tooling cost and making the tooling and the part pricing just a little bit more expensive. Um, it's not impossible to do. It's just you have to know that there's a lot more steel and a lot more machining, a lot more labor involved to do these holes that are perpendicular to the line of draw in a particular part. Um, so determining where the parting line falls on the part, it's best that the parting line location is one that allows the tool simply to open and close. And if you have to have a parting, or if you have to have a component or geometry or a hole such as this that's perpendicular to that parting line in any way, it can be done with slides, but it does increase the cost of the tool a little bit. Doesn't mean if you need that functionality, you shouldn't design it into that. Just know that ahead of time that that's going to be the case. Um, Also, I want to talk a little bit about draft. We're going to take a look at this part from the front. And what I'm going to do is up here on the top, the side that we said, what you probably shouldn't do. Basically, I'm going to draw a line, and the right edge of this box is a completely vertical line. And you can see that that top half is completely straight, has no draft. And what happens is when you go to pull that part out of the cavity, this entire surface drags on the steel the entire way out. And if you've ever tried to take two 5-gallon buckets apart and they've kind of vacuum locked on you, you know that that's a pretty impossible situation. It takes a lot of force to get some air in there to break that and to finally get those buckets apart. Same thing happens with your injection molded parts. If you don't put draft on them, it becomes really a higher level of force required to push the parts out. And when you're using ejector pins and you're pushing really hard, oftentimes you can misform or warp the parts as they're still a little bit warm. They're not 100% cooled. And if draft is added, it makes it much easier to push the part out of the cavity. And so what I'm going to do is the same exact thing. I'm going to say that the right edge of that blue box that I'm drawing, and you can see in the part that it's drafted down, the minute those ejector pins push this just a little bit, it breaks that surface, and the part is much, much easier to get out, requiring much less force. And that reduction in force basically gives you a more repeatable and more desirable part. And what I want to do also, so now what I just showed you was the draft on the cavity. What I want to show you now, let's see here, what's going on. Let's try this, maybe. Nope. Well, this will show it. Yeah. Okay. So what I want to show you now is also that the inside of this part has draft as well. I'm going to draw a box that goes up inside the tool. And now what we're looking at is the left edge of this green box compared to the geometry of the part on the inside. And you can see that there's draft on that component as well. And so successfully demonstrating, what a typical draft would look like on a part, and a part that will eject much easier and have less warp and better repeatability and better part appearance as a whole. So basically, you should basically apply draft to the cavity of the tool, and you should also apply draft to the core of the tool. And I'm going to switch real quick to that that tool again. And we're just going to pull up this B cavity once more. And we're going to run a section through there. And I know this is probably obvious, but once again, we can draw a box. And it's a little harder to see with that blue on there. Hold on a second. There we go. So once again, we're going to draw our box, and we're going to see this is the reverse of the modeled part, but you can see the draft on the right edge of that relative to the part there. And then we're going to draw a green box here, and you can see on the left edge compared to the tool geometry that we have draft on the core. This surface, these surfaces being the core, right? That has draft. And then also the cavity all has draft as well. So that would be a well-modeled part as it relates to draft, and it would be very easily ejected with the minimal amount of force. Okay, what else are we going to talk about today? We talked about subgates. Like I said, this is a very intense topic, in micro injection molding, and the subject matter is vast, and there's a lot of details as you dive down a rabbit hole. But right now, we've been kind of showing a subgate. We're going to open up the runner here and show you that the molten resin comes down the runner, which is to about right here, and then it dives down this funnel, which is this cone, which is basically below the surface of the parting line, and then when it punctures through that cavity wall, it becomes the gate or the entrance for the molten resin to come in. And this is a subgate. There's also parting line gates, sometimes called tab gates. When your part does not have the ability to have a flat surface to put a subgate on, you can do a tab gate, but typically the runner and gate eject together with the part, and they're still connected. And then so an operator would then need to either twist the runner and gate to get them separated, which is an additional labor step, which is something any and most companies would charge you for, or maybe it needs to be really tight to the surface of the part, and then you'd have to have a special clipper to clip that part off. So it's always beneficial to design a subgate as opposed to a parting line gate or a tab gate. But if the geometry of the part doesn't allow it, we can always create a parting line or tab gate. There's also cashew gates, valve gates, and direct gates. But today we're simply focusing on subgates. I think we've already talked about this, but we'll just touch base on it real quickly again. Might be something we already talked about, but we have a flat surface. The other thing I wanted to chat about was you want to place your gate in the thickest portion of your part possible. And so when we did a section view, we'll see if we can get a section view for where the gate's going through. You'll notice that I put the gate here, and up here it's only 10,000ths of an inch thick, but down here, let's just say it's roughly 30 thousandths thick when it's all said and done. Anytime you put a subgate on a surface, you want to do it in the thickest portion of the part, and that will help with resin flow, and it will help create a part that you can fill and then pack and hold the shape a little bit better than if you injected into a very thin section of the part. Basically your gate diameter, if you wanted to sketch that in for yourself on a part, we have a DFM team that will review this, and there's a lot of different factors on how and why this changes. But if you want to know what this diameter is, a rough rule of thumb would be the diameter of that gate should be at least half of the thickness of the part. So in this particular instance, I believe that's what we have on that part. So ejector pins, I would say in this particular instance, I tried to keep this feature as small as I possibly could, because anytime you make that feature bigger, it's going to take more resin. It's going to, be a thicker part of the tool, a thicker part of the part. And it's some of these resins, some resins are $1 a pound, some of it's $1,500 a pound. So whichever resin you're using, you want to try to minimize that as possible. So I try to keep this feature as small as possible, and that's the smallest diameter pin that we can do. But in general, if your part will allow a larger ejector pin than 15 thousandths, the larger the better, whatever the geometry would allow as it relates to ejector pins. If you're using 15 thousandths ejector pins in as part of your design plan, then you'll have to have more. You certainly wouldn't want to try to push this part out with 3 ejector pins. Um, the higher the number of ejector pins at 15 thousandths, the better. But if, let's say, your part would allow a 60 thousandths ejector pin in 4 corners and it could equally lift that thing out, and you asked me which one you'd go with, 15 thousandths at 7 or 60 thousandths with 4, I would certainly pick the 60 thousandths with 4, as long as it can equally lift it out. That gives you a little bit longer tool wear as far as those ejector pins and having to replace those ejector pins is concerned. So that's my opinion on that particular matter. I want to shift over to the slide detail a little bit. We'll switch back over to the tool design, and what we'll do is we'll collapse this and we'll turn these back to transparent. And so, we decided that we needed a hole, and that hole was perpendicular to the parting line axis. In this particular model, it's the y-axis, but you'll see that this core pin, this blue core pin that's on the end of this slide, is in the x-axis. And whenever that happens, typically there's a slide system that's actuated mechanically. In this instance, we would have a pin that goes through there, and when the mold opens, that pin would be at an angle and it would push this slide back. And typically, as we open the mold, we slide that slide back, and then we eject after that core pin has cleared that hole. This is a thing that people do all the time, putting either full circles in or just geometry that have an undercut. But that would be an example of a slide and how a geometry feature perpendicular to the axis of the parting line is created. The last thing I want to chat about before we wrap this up is there are a lot of questions always about surface finishes. And in the micro injection molding sphere, a lot of the cavities are burned utilizing electrodes and EDM machines. And our EDM machines are capable of producing a EDM fine surface finish, which typically lands, there's a surface finish SPI standard D1 and D2. This finish is a smooth matte finish. It's included as a standard finish with no upcharge. And a lot of the projects kind of land in that direction. There are some parts, however, that customers want a glossy finish on for either form, fit, or function. And so we can also go in and do a post machining polishing, and we can polish up to SPI standard A2 through C3 and any of the steps in between. And but I would let you know that most companies, if you're not accepting the as machined or the EDM fine finish, anytime you apply a tool maker to go in and polish the surfaces of the cavities and or the cores, there's a little bit more labor charge, and it is an upcharge service, which increases the cost of the tooling. So I think most companies would charge for polishing something to a mirror finish, giving you a smooth finish on a part. Also, on surface finish, you can do some custom texturing. Some of the processes utilized to do this are chemical etching and or laser etching. And there's a lot of things that you can do to do these post-mold etching and post-mold either chemical or laser etching to give your part a different texture and or finish. Now, I would tell you that that's not for every part. Some of these parts are very tiny. If you have a part that's 20 thousandths in diameter, and maybe an eighth of an inch long, it's oftentimes difficult to get chemical etching or laser etching in a cavity that small. But it's on a case by case basis. I'll also tell you that custom texturing is also an upcharge service, and it will increase the cost of the tooling, and also it will increase the lead time because there's an involved process to make that happen. And then the last category of finishing that I'll share with you are typically for optical parts. And you have a formula for these surfaces that you would like to have very clear, very transparent. And typically, what has to transpire there is that you have a nickel plated core that is then diamond turned with very precise equipment. And again, I said this finish is typically used when you're molding optical parts, and there's an upcharge for this service. It increased the cost of the tooling. It's something that we do on a day in, day out basis. We do a lot of optical parts, but it does increase the lead time and the tooling cost. But if you need a perfect mirrored finish in a very specific shape and or formula, there are finishes that can be done for the core pins and or the cavity surfaces that are available in that specialized finishes category. Hey, that's been probably our 15 minutes. I hope that this was beneficial for you, that somewhere along the line that you saw something maybe that you didn't know or picked up a tidbit of information that was helpful for you. Thank you for your time. I appreciate it, and thank you very much.